Friends, hello everyone. We continue with training videos dedicated to the CRISS CPM computer. Amateur radio computer. An 8-bit computer built on a modern element base. That is, this is a computer of the 21st century, it is not retro. This is a completely independent computer, but which can run many programs from well-known ancient computers. Only typical components. The computer is described in more detail in the radio magazine. There is a technical support site and several communities where they will always help you. In this video we will talk about the ROM chip, which is highlighted in the picture with a green spot. In the story about how to use the system panel, the proposal unit turned out to be a little blurry, so we will now catch up here and let's try to figure out what kind of idea there was when this ROM chip was added. The ROM chip hangs on the general SPI bus of the computer and has a size of 128 kilobytes. So, let's talk about what it is for and how to work with it correctly. Our computer is running. To make it easier to see, today the keyboard has been placed separately. To make it clear what we are pressing. The picture on the left is not an emulator, it is a special video capture card that shows a live picture, which the computer produces. So let's begin. What is a ROM chip needed for? The magazine said that it was mainly needed to work with 2 user sessions, but in fact the situation here is a little more interesting. We boot the computer, select a certain operating system image. Here we receive a certain set of commands, launch something, get. Our development environment. At any time we have the opportunity to enter the system console, select the section. I'll call EEPROM and give command A. That is, we write our RAM to the bottom 64 kilobytes. The 2 blocks shown here, 1 and 2, are the bottom and top 64 kilobytes of ROM. Now we find out that we need this. We reboot the computer. As a reminder, Ctrl-Alt-Shift-Escape works as a reboot command. Here. And now you see that we can. It offers us to boot from the EEPROM, from block 1 or 2. Select A. We boot from the EEPROM and immediately find ourselves in our saved user session. Accordingly, you work, you saved, you left, some analog. A kind of analog of the sleep mode on a computer. They calmly turned off the power, turned it on again, and came back. This is the first option on how to use it. This option can be expanded a little. How does this happen? And let's go through it all again. We reboot the computer, boot from the operating system image. Now, let's save it. A. We stored it in block 1. D. We saved. What is it for? There is a magic key combination Ctrl-Alt-F. We find ourselves in the first user session. Попадаем в первую пользовательскую сессию. Здесь мы, например, запускаем какой-нибудь редактор and open some file. Here we have our working file. Now we switch to the second user session. We go to the disk where we have the compiler. The C compiler is here. Accordingly, we can now compile this program. Our program has compiled. Let's try to launch it. Here we get it. Press Ctrl-Alt-F. Let's go back. Now we can fix our code, save the result, return to the second session, where we have a compiler, and repeat the same thing. Subtitles made by Dima Torzak. We see our result. It is very convenient in terms of development, because at the same time there are two user sessions, you actually have a complete development environment. You have both an editor and the compiler itself greatly speeds up the work. This is the first plus. Second, why was another microcircuit needed? And what else is interesting about her? CRISS's computer has the option of assembling it without a peripheral unit. That is, the minimum efficient computer configuration. In fact, this is our central processor and memory chip. After that, when the computer starts, it starts polling for. Poll all our devices and see what was found and what was not found. This is reflected on his home screen. First it checks the memory, then it checks what version of our computer it is, and then it checks if there is a peripheral controller. Control of peripheral devices works for us with the keyboard, output to the screen works through it, the mouse works through it, GPIO works through it, and the COM port hangs on it. If suddenly we don't have this controller, and we don't have the SD card either, from block A of our ROM and launches the program with which
нашей ПЗУшки и запускает в работу ту программу, с которой
you were working at the moment it happened. Processing done a little differently. Keystrokes, that is, if we are waiting for a key to be pressed but we do not have a peripheral device controller, the computer behaves a little differently. Returns virtual clicks with non-existent code and the program can process this. Therefore you can develop a program on a normal computer, then connect the expansion unit on which all the cards are located to your computer, which is assembled in a minimal working configuration, upload information there. A ROM chip, but, of course, it is assumed that it is installed there, we saw the information there and after that, when you turn it on, it will automatically launch the program and work with it. This is the first block. The second block that we have is intended to be used so that the client program can access it.
По задумке используется для того, чтобы программа клиентская получила к нему доступ.
It's very simple. Literally several pins per port. Here a small program has already been made.
Небольшая программка уже сделана.
Let's go over it. Anyone who has read the description of the computer remembers that there are special data blocks, the work with which is based on the same principle. First we go to the port address. Here we have FC, we write the address in this data block. Then everything we write to port FD we sequentially write or read, no matter what we write or read the port and. The pointer will move by 1 each time. Accordingly, the FC block is responsible for working with external SPI devices, and we sequentially write the device code there. 0C is the ROM code, then a special setting for the access speed. You can leave 0 by default. It will work at a frequency of 5 MHz. This is quite enough. Next we give a command to read, then we write down a certain address to which we will read. Accordingly, these are the most significant bits, the least significant and least significant. By writing a 1 to the most significant byte, we will work with the upper half of the memory. After this we issue the command. FE is equal to 0, this command executes a request to the SPI device and after that, just like we wrote, we read back the data that we received. This is what we see at the entrance. Accordingly, this is the package that we prepared and sent. This is the package that we received back, that is, this is a certain piece of code that we made. Therefore, if you have a CRISS used in the control system mode somewhere, then the second half of the ROM is perfect for recording information about the current state there, in order to write logs there. In general, everything that is necessary, as practice has shown. This is more than enough. Circuit and CRISS boards designed for embedded devices, that is, where we do not have communication interfaces with a keyboard, with a monitor, and so on. Look in magazines. Radio according to plans for the 24th year. Such an article should contain a detailed description of how to work, how to divide the CRISS into 2 parts and how correctly build your control systems based on this computer, since it is a very good alternative to the same Raspberry, for example, in terms of functionality. Approximately the same interfaces, but much easier to understand, configure, and operate. Here, in fact, is everything you need to know about working with ROMs. Only interesting ones. Therefore, the CRISS CPM computer is absolutely real, just small. Friends, thank you. Until new videos. Subtitles adjusted by Simon.